Welcome to Chapter 10 of Class 9 Science, Work and Energy. In this fascinating chapter, we'll explore the scientific meaning of work, discover different forms of energy, understand how energy transforms while always being conserved, and learn about power, the rate of doing work. We'll see how these concepts explain everything from simple daily activities to complex natural phenomena. Get ready to look at the world through the lens of physics. Let's begin with understanding the scientific meaning of work. In our daily language, we use the word work very broadly: studying hard, pushing heavy objects, carrying loads. We call all these activities work. But in science, work has a very specific meaning with two essential conditions that must both be satisfied. First, a force must act on an object. Second, the object must be displaced in the direction of the force. If either condition is missing, no scientific work is done. For example, if you push a wall and it doesn't move, you might feel tired, but scientifically, you've done no work on the wall because there's no displacement. Similarly, if you carry a heavy load while walking horizontally, the force you exert is upward, but displacement is horizontal, so again, no work is done on the load. Understanding this distinction is crucial for studying physics. Now let's learn how to calculate work done. When a constant force acts on an object and causes displacement in the direction of that force, the work done equals force multiplied by displacement. The formula is W equals F times S, where W is work in joules, F is force in newtons, and S is displacement in meters. 1 joule is defined as the work done when a force of 1 newton displaces an object by 1 meter in the direction of the force. This unit is named after James Prescott Joule, a British physicist who made important contributions to thermodynamics. Work can be positive or negative depending on whether the force and displacement are in the same direction or opposite directions. For example, when you lift an object upward, you do positive work, but gravity does negative work on it. Now let's explore the concept of energy. Energy is defined as the capacity to do work. An object that possesses energy can exert forces on other objects and cause changes. The unit of energy is the same as work, the joule. When work is done on an object, it gains energy, and when an object does work, it loses energy. Energy comes from various sources. The sun is our biggest natural source, driving weather patterns, plant growth, and even fossil fuels which store ancient solar energy. Other sources include nuclear reactions, the Earth's interior, tides, wind, and water. Energy exists in many forms including mechanical energy, heat energy, chemical energy, electrical energy, and light energy. The ability of energy to transform from one form to another is what makes all processes in our universe possible. One important form of energy is kinetic energy, the energy of motion. Any moving object possesses kinetic energy. A speeding car, a flying aircraft, flowing water, blowing wind, all have kinetic energy. The kinetic energy of an object depends on both its mass and its velocity, but especially on velocity because kinetic energy is proportional to the square of velocity. This means if you double an object's speed, its kinetic energy becomes 4 times greater. The formula for kinetic energy is E_k equals 1/2 m² squared. We can demonstrate kinetic energy through simple experiments like dropping balls from different heights onto sand. Higher drops mean more kinetic energy and deeper dents. The work done on an object equals its change in kinetic energy, which is known as the work-energy theorem. Another crucial form of energy is potential energy, stored energy due to position or configuration. There are different types of potential energy. Gravitational potential energy comes from height above the ground. The higher an object is lifted, the more potential energy it has. Elastic potential energy is stored in stretched or compressed objects like rubber bands or springs. Chemical potential energy is stored in chemical bonds in food, fuels, and batteries. The formula for gravitational potential energy is E_P = mgh, where m is mass, g is acceleration due to gravity, and h is height. It's important to note that potential energy depends on the reference level you choose. The same object can have different potential energies relative to different reference points. Energy constantly transforms from one form to another in nature, and this is where we encounter one of the most fundamental laws in physics, the law of conservation of energy. This law states that energy can neither be created nor destroyed, it can only be transformed from one form to another. The total energy before any transformation always equals the total energy after the transformation. For example, when an object falls freely, its potential energy decreases while its kinetic energy increases, but the sum remains constant. Green plants transform solar energy into chemical energy through photosynthesis. Wind turbines transform kinetic energy of wind into electrical energy. Our bodies transform chemical energy from food into kinetic energy for movement and heat energy to maintain body temperature. Understanding these transformations helps us harness energy efficiently. Now let's discuss power, which is the rate of doing work or the rate of energy transfer. Power tells us how quickly work is done. The formula is power equals work divided by time, and the unit is the watt, named after James Watt. 1 watt equals 1 joule per second. When we say someone or something is powerful, we mean they can do work quickly. For example, if two people climb the same height, the one who takes less time is more powerful because they do the same work in less time. We use larger units like kilowatts for bigger power ratings. In electrical contexts, we often use kilowatt hours to measure energy consumption. Understanding power helps us compare the efficiency of different machines and processes. As we conclude this chapter, let's review the key concepts. Work in science requires both force and displacement in the direction of the force. Energy is the capacity to do work and exists in many forms that can transform into each other. The law of conservation of energy states that energy cannot be created or destroyed, only transformed. Power measures how quickly work is done or energy is transferred. These concepts help us understand everything from simple machines to complex natural phenomena. They're fundamental to physics and essential for understanding how our world works. Remember these principles as you observe energy transformations in your daily life. Undefined.